What is calculus? Calculus is a scary subject to many students, but it can be made easy and actually needed by engineering students. It's considered intermediate math, a bit more complicated than algebra and trigonometry, and they're still more abstract and more difficult to comprehend, like abstract algebra, differential equations, combinatorics, and number theory. We'll have to learn new operations. Like in algebra, f sub x equals log 10 sub x there. And in trigonometry, example of a trigo function, tangent theta equals sine theta over cosine theta. What is calculus? Why do engineering students need to learn it? Well, it developed out of necessity. So let's visit history to see what necessitated the development of calculus. The Greeks started to study shapes and their characteristics. They found out how to calculate the area of polygons by dividing its shape by triangles, and they know the area of a triangle. The trouble came when calculating the area of a curved shape like a circle. Here, there are no vertices from which to draw a line, so it cannot be split into triangles. By this, they developed the method of exhaustion, where they can insert a triangle and then gradually increase the number of sides from 3 to 4 and so on. Let me show you. As you can see, the shape is looking more and more like a circle. The area of polygon is nearing the area of the circle. Though it can never get there, we need an infinite number of sides to have the area of the circle. So we can say that in the limit of infinity, the area of the polygon is equal to the area of the circle. Though the Greeks did not fully grasp the notion of limits, they were able to develop this rudimentary technique and prove the area of a circle this way. Area equals pi r squared. It is precisely this kind of logic that we will use to calculate the area under this curve, f sub x. Just like the circle, we can approximate the area, only this time using rectangles. The more rectangles, the better approximation. We'll just make the rectangles narrower. We can say, in the limit of infinitely thin rectangles, we can find the precise area under this curve. So clearly, there's something about curvature that specifically requires calculus. We can easily calculate the area of a rectangle because the distance between opposite sides is fixed. But when that distance isn't fixed, we need a new, more sophisticated technique to find this area. So, how did calculus develop in the 17th century? French mathematician Pierre de Fermat started the development, but it was Sir Isaac Newton along with Gottfried Leibniz who were credited with developing modern calculus. Newton developed calculus simply out of necessity to have the tools he needed to solve problems in physics regarding celestial motion. Leibniz started 1 year later, independently of Newton. It is his notations that we still use today. Newton observed that falling bodies like an apple have velocity that will increase every single instant until it hits the ground. But up to that time, that object must have a definite speed at any given instant. He knew of no mathematics that can adequately calculate these instantaneous velocities, and something had to be developed that can describe the difference between the value of a function, in this case, position, and the rate of change of that function, in this case, velocity. So we can see this concept, rate of change, was the other of two important parts that brought about this mathematical revolution, as its exploration comprised the development of differential calculus. This is in contrast of the first one we discussed with the area under the curve which are rectangles. That is called integral calculus. However, both differential and integral calculus involves the concept that we can do something infinitely many times and get a finite answer that is useful. Also, both involve things that are infinitely small or are infinitely close together. Although it took until the 17th century to get this in a rigorous and formal way. Calculus is pretty much the same idea which have been pondered by ancient Greece. So here's one example. A form of Zeno's paradox says that in any one distance of time, an arrow never reaches its target, as it must infinitely occupy one half of the distance between its position and the wall. The introduction to calculus, we're ready to go to lesson 2. But before that, let's have a learning assessment.